Hi guys. I hope everyone is doing so great. Okay, so welcome to today's session. So in today's lesson, we are going to still move on with the discussion of functions. But in our previous lesson, we learned how to find domains of different types of functions. So today we are going to learn how to work out then the range of different types of functions. You see that? So in order to understand and know effectively how to work out the range of different functions, we shall first discuss one of the basic things that you should know when it comes to the representation of functions explicitly. You see that? So one of the things that we have come to realize is that most of the time when we have a representation of a function explicitly, it always comes in the following form. You see that? So it will be f of x is equal to some expression that comes afterwards. You see that? So this is how mostly our functions that we have been playing around with will always look like. And examples involve f of x is equals to 3x minus 4. F of x is equals to 3x squared minus 5. And this is what we have been used to so far. But one of the things that you should know is that there is a nice way actually of representing functions. You see that? And a nicer way of representing function, it goes as follows. So you should know that NB. So one thing that you should know is that this thing that is called f of x, which is usually called the name of the function, can actually be replaced by the variable y. You see that? So every time when you see f of x, this is equivalent to just replacing this with the variable y. And if you replace this with the variable y, it means these functions that you have here that I've used as examples can be rewritten as just saying f of x is such that y is equals to 3x minus 4. Or you can write also that one as f of x is equals to y is equals to 3x squared minus 5. So this is one of the things that you should know, that every time when you're given the explicit equation that represents a particular function, you can simply get rid of the f of x name and replace that with y. You see that? So the reason why we want to replace it with y is because it allows us to transform a function to become an equation in some way. You see that? So one of the things that you must be aware of as far as maths is concerned, a function and an equation are two different things. You see that? So an equation is something which has variables that can be found, whose values can be established. While on the other hand, a function is not necessarily an equation. It's not something that you can solve for. So the x that we find in a function can take anything, while the x that you can find in an equation can only take specific values. You see that? So that's why now we'll try to prefer then to say, let's work out, let's try to shift from working with functions to put functions as algebraic objects. And to do that, we just replace f of x with y. You see that? So the reason why we want to do this, it is because we want to use the skills that we have learned from solving equations to find what is called the range of a given function. You see that? So that's what we're going to see today. So we are going to practice a procedure that can be used to find the range of any function. So I'm not going to look at function in the categorization that we used mostly when we were discussing domains. So when we were discussing domain, we looked at different classes of functions. And the reason why we did so was because each class of function, there was a certain procedure that has to be followed to establish the domain. But now when it comes to the range is something that can be established as long as you know the goal of what you have to achieve to find the range. You see that? So what exactly is the range? What exactly is the range? You see that? So to understand exactly how one can define a range is, let's consider maybe an equation of the form. You see that? So let's consider an equation of the form. So consider a function of the form. So let's say you have a function which now is written in the form y is equals to something, where this something is some algebraic expression in terms of x. You see that? So let's consider a function which takes this kind of structure, where y is made the subject, and on the other side we have an algebraic expression mostly dependent on x. It doesn't necessarily have to be x. It can be any other variable which is the independent variable in that particular situation. You see that? So let's say maybe you have something like this, and then you are tasked with the problem of finding the range of this particular function. So now let's understand exactly what is the range. So when you are asked to find the range of a function, what exactly are you looking for? You see that? So to find the range of a particular function, you should understand that what we call the range is something which is defined as follows. You see that? So the range of a function represented in this form is a set of all the y values for which the resulting equation is solvable. You see that? So we have already discussed that every time when you have a function and you write it in this form that we have here, it gives a function the structure of an equation. But this is not yet an equation because you have two variables already in the same sentence, making it an equation that one cannot just simply solve for to get all those things. You see that? So when it comes to finding the range, the range of any function represented in this form is all the set of y values for which when you plug them there, you will always get the solutions to those equations that are created. Because every time when you put a certain value for y, you will always get an equation which is purely dependent on x. So if that equation is solvable for the y values that you'll be just putting in there, then their collection is what we call the range. You see that? So when you have an understanding of the range in this way, then it becomes so simple to find the range of any function that you can think of. You see that? It's just that, yes, when the functions become complex, the equations that you have to solve for also, they become quite complex. But in order to demonstrate exactly how we can use this kind of reasoning, or how actually we can use this idea to find the range of different functions, we are going to look at the following examples. You see that? So the examples will be extracted from all the different functions that we're already familiar with. You see that? So the first example that I'm going to use is going to feature a parabolic function. So it's going to feature a parabolic function so that we can see exactly how we can try and establish the range. So given a function f of x, which is defined as 3x squared minus 2x plus 1, determine the range of this function. You see, so this is the question. You are given this parabolic function, and the question says, determine the range of this function. So how will you go about determining the range of something like this? So to go about determining the range of something like this, we'll use the ideas that we have built. So we know that this particular function can be written as f of x such that y is equals to 3x squared minus 2x plus 1. This transforms this thing completely into an equation. You see that? So from the fact that now f of x has been replaced from y, it now follows that we have 3x squared minus 2x plus 1 minus y is equals to 0. So now we see that we have a quadratic equation in x equal to 0. And now our task is to find the range. So remember now, this is time to recall exactly what do we mean by range. So remember the range, it is the set of all values for which this equation is a solution. You see that? But you know that to find something like that can be quite tasking. So the best way to answer problems that involve the range is always to look at the opposite side. So instead of you trying to find values for which this equation is solvable, you can just simply look at the question of finding all the y values for which this equation is unsolvable. You see that? So now, if we look at this equation, what do we know? You see that? What do we know? So, we know that this equation is unsolvable if b squared minus 4ac is less than 0. So we know that what we call a quadratic equation, this is the nature of the roots thing that we met in high school. So it's coming back now. So we know that an equation like this one can have unreal solutions or cannot have solutions every time when the discriminant is less than 0. So what does that then say? So since the equation in x, it follows that b squared, which is minus 2 squared minus 4 by a by c is less than 0. So this implies 4 minus 12, 1 minus y is less than 0, which implies that 4 minus 12 plus 12y is less than 0. So we know that 4 minus 12, it's minus 8. So we throw it out. So we get 12y is less than 8. Therefore, we can see now that y is less than 3 quarters. You see that? So which means this equation is solvable for all the values of y which are less than 3 quarters. So it's not solvable. So for all these values that are less than 3 quarters, that equation has no solutions. Which means it must have all solutions for all y values which are greater or equal to this value. You see that? So that's the equation is solvable if y is greater or equal to 3 quarters. So therefore, what is the range? So the range is what now? So therefore, the range that we're looking for is everything from 3 quarters to infinity. So that forms then the range of this particular function that we are looking for. So knowing the values for which the function is not solvable will actually give us a range for which the values for which the function is solvable. So that specifies now the range that you are looking for. So this is the range of our equation. Okay, so let's do another example so that we can practice this technique of finding the range and perfect it. So the next question goes as follows. So this question will feature an exponential function. So this question will feature an exponential function. So it goes as follows. So given that a g of x is the function 2 to 3x minus 3, determine the range of gx. So how can we go about finding the range of this g of x function that we have here? So first we recall that g of x is such that y is equals to 2 to 3x minus 3. You see that? So that's what we see here. Definitely, since this is an equation, now I can do some algebraic manipulations where I get 2 to 3x is actually the same as saying y plus 3. Then now, so if you look, the logic is always to introduce y into the function and then make x the subject. So every time when x is the subject, it's easy to actually tell which whether the equation is solvable or not. But the techniques also it depends on what exactly you're dealing with. You see that? So now for an exponential, we'll try to make x the subject. And now we know that every time when we want to bring down this x, I have to introduce the logarithm. So I'll introduce the natural log to mean that 2 to 3x is equal to the natural log of y plus 3. You see that? Then from here now, we know that this means 3 to x ln 2 is equal to ln of y plus 3. But now I don't need to worry a lot about a lot of things that are happening here. But first we must pay attention to what exactly happened here. So this follows from the fact that ln of a to n is equal to n ln a. So this is how we establish that result that we have there. But now to find the range, we just have to pay attention here, because that's where we have the y. Now what do we know about a logarithm? We know that a logarithm will always give something out when the argument is non-negative. But when it's 0 and negative, you can't actually get anything out. You see that? So therefore, this equation is only solvable if, so we know that this equation is solvable if y plus 3 is actually greater than 0. Otherwise, if y plus 3 was going to be 0, it's undefined, or if it's negative, it's undefined. So this implies in this case y is greater than minus 3. So now since we looked already for values for which the equation was solvable, it means this what we have here is the range. So therefore, what is the range of gx? Is everything from, so we use a round bracket now, so it's everything from negative 3 to positive infinity. So this gives us the range of this function. You see. So now we know what the range of this function is. So let's do also more examples so that at least we can be effective in how we use this procedure. You see that? So the next question that we have goes as follows. So this question is going to feature a hyperbolic function. But this doesn't mean that this procedure only works when you're dealing with these functions that I've used examples on. It will always work on any function that you will have. It's just that now you just have to pay attention to what structures are present there, because all the structures that I'm dealing with are things that you can find. You can find exponent in equation, you can find rational fractions in equations, and you can find just simple things like logarithms and stuff. So you just have to know how to actually use those things to find the range. So now what is given now is we are given a function h of x, which is defined as 3 over x minus 5 plus 4. You see that? Determine the range of h of x. You see, so that's what we want now. So how do we then solve for this? So to solve for this again, we recall that h of x is such that y is equal to 3 over x minus 5 plus 4. Now we know the goal is to make x the subject, so we can cross multiply. So this gives us y bracket x minus 5 is equals to 3 by 4 bracket x minus 5, where we have actually cross multiplied throughout by x minus 5. Then here this side I get xy minus 5y is equal to what? Is equal to 3 plus 4x minus 20. Remember, our goal is to make x the subject, so let's make x the subject. So we take everything with x one side, so we have xy minus 4x is equal to 5y minus 17 that side. Now pull out x this side, you'll get y minus 4. Then this is equal to 5y minus 17. So what is x? So we see that x is 5y minus 17 over y minus 4. So if you check now, we have a rational fraction. So now, when can x be true? When can we have solutions? You see that? So we know that the solutions to this equation can exist if y minus 4 is not equal to 4 is not equal to 0. So we know that we'll always have solutions every time when y minus 4 is not equal to 0. So this implies y must never be equal to 4. So we see that every y can work but except 4. So therefore, what is the range here? So therefore, the range in this case is simply everything excluding 4. So it's negative infinity to 4, then we skip 4, then we go from 4 to infinity. So this provides us with the range of this function, you see. So yeah, that's it with finding the range. So you can apply this technique in any function, and you can always get the range that you're looking for. So thanks for watching. We'll see you on our next lesson together. Bye.